Hello, in this video, I want to have some discussion about how to determine the number of factors in the exploratory factor analysis using R. So the number of factors is an important task you have to do in the EFA. So the idea I have here is I want to write an R function that generate a data set for factor analysis in which I can actually specify the number of latent factors in the data set. Okay, so let me load in the library mass, and then this is the function called the generate factor analysis data. It asks for the sample size and the number of variables, number of factors, and factor loading range. I will use a uniform distribution, the sampling from 0.4 to 0.9. Noise variance is 0.2. So I'll add a noise term when I created the data. Okay, so you can see in this function specify a loading matrix and then assign these loading factors by randomly sampling from uniform distributions with the given range. Okay. And then so observe the data is this. Then you sample the latent factors based on the number of factors and the number of sample size, and also the sigma matrix. Okay. And then the observed data is the latent factor multiplies the transposed loading matrix, okay, plus an noise term. And then this is the column names. So let me run through this function. Okay, now it's in there. Set a random seed. Let me generate the data for sample size 100, number of variables 10, and factors n. Okay. So this is the data set we created, the first few rows. In this video, I really want to introduce you to this great R package called the EFAtools. Okay. Be careful, the letter T here is a lowercase. Okay. If you use the uppercase, I will tell you this package cannot be found. Okay. So let me load that library, and I'm going to use the n_factor function, which the help documentation is on the right hand side. You can see this package is inside, this function is inside the EFAtools package, and it's for various factor retention criteria. And highlight there, you can see there are CD, I think, EKC, whole, KGC, parallel, SGRE, and SMT. Okay. So I don't have time to go over the technical details of each and every method listed here, but see, this function is pretty powerful. It has included all these methods. Okay. And let me run here. You can use n_factors function and just put the data frame in there, but you must specify method equal to ML. Okay. And this is what it looked like. It's running. All right. You can see there's a comparison data that's the CD and the EKC. It's a whole method. There's 3 variants of whole method, and there's a Kaiser Gottman criteria and a parallel analysis, and the scree, and also, oh, there's something called a Kayaki information criteria. Okay, so this is why we need to we must specify method equal to ML, because you want to compute the AIC value here. And on the right hand side, it also generates the scree plot as obviously showing an elbow shape. Okay, so 1, 2, 3. But then you can choose the first two there. You can see most of the methods in this function gave 2 as the estimate, and the AIC gave a little bit overshooting a 3. Okay. It is very difficult to predict whether we'll get a good, accurate estimate of the number of factors, because the data sets are so arbitrary and unpredictable. Okay, and we don't have clear conditions under which we will have certain number of factors. Okay, so this is actually can be a research project. I think you can do a lot of simulation studies. You can also maybe do a methods assemble of all these methods to improve the accuracy of the predicted number of factors. But here I just want to share an online source with a rule of thumb. Okay, so the number of factors depends on many different factors like sample size, the sample size to number of variable ratio, the number of variables to number of factor ratio, etc., etc. Okay. Okay, I'm going to lead you to that online source. So, okay, this is the online source on LinkedIn. Check the suitability of your data for factor analysis. So the highlight here, it says, a common rule of thumb is to have at least 10 observations per variable, or at least 3 variables, and at least 3 variables per factor. And second, you should ensure your variables are measured on the interval or ratio scale. So if you have binary data, mixed data, ordinal data, this estimate of a number of factors may become even more inaccurate. Okay, and they're normally distributed, etc., etc. Okay, and also the strength of correlations also matters. So you can see there are many different underlying factors impacting the number of factors. Okay, but there's no like exact rules. So let me modify this data set a little bit. Say now I want 3 factors, still 100 sample size, 10 variables, and then I run the n factor again. Now you can see, even though the true number of factors is 3, it start to become inaccurate, right? So this is most of them point to 2 and some point to 1. So they're all underestimating the number of factors. So let me see if I increase the sample size, for example, increase to 500, what is going to happen? Sample size, increased sample size does help. Now we have correct estimation for the number of factors. But let's push our luck a little bit more. So let's say we want to try 4 factors. So now it doesn't meet the rule of thumb because we only got 10 variables. Okay, so let's just try. It's still doing pretty well with the majority, but then you got 2 that are underestimating. Let's push our luck again. Let's try 5 factors. And now it's really all of the estimates are underestimates. So there's a kind of limits this method can do. It really depends on the underlying structure of your data set. Okay. Sometimes it just doesn't make sense that there will be accurate estimate for the number of factors. Okay, I hope this video give you some idea about how to determine number of factors in EFA. Thank you.